all. So please welcome back Moritz KASSMANN.
Thank you. Wow. You know, this is the way you do it in China. When you give a talk in China, in a conference or in a seminar, there's applause before the talk. It's totally standard. Every talk starts with an applause. So,
but do they do also after?
That depends. All right, we have 1 hour, and everybody wants to go outside and have lunch. So I will not go over time. I discussed with Azahara what to do, and I told her. I mean, she invited and paid for the music, so she can decide what piece she gets to listen to. And so what we will do, I will give you one example. This will be chapter 5 about non-local to local convergence. And then in chapter 6, within 45 minutes, you get like a very colorful picture about local regularity and a history spanning the years 1882 until very recent, like a couple of weeks ago, where I hope to be able to convince you that now, after 150 years, we have a full understanding of something which began in 1882. So this will be the remaining 45 minutes. Okay, so the one example, that's basically the one that I had scribbled down at the lower right corner. So I want to tell you how you can approximate a local problem, a solution to a local problem, through solutions to non-local problems. So let's pick a coefficient matrix A, where A of x is a symmetric matrix, and as a function of x, it is bounded and uniformly positive definite. So the lower bound says that it's positive definite, and that bound does not depend on x, and this is the upper bound. What you say is strictly elliptic situation, so perfect. But no regularity in x. Yeah? Now let's pick a solution to a general Neumann problem for this corresponding divergence form operator. And in order to optimize, let's directly jump at the weak formulation. Yeah? So we pick a right-hand side f in H1 perp d prime, and we pick Neumann data in H1/2 prime. We call it capital F and capital G, and we assume that U in H1 perp omega, which is D, satisfies this equation. So this is the weak formulation of the PDE. This holds true, I assume it holds true for every test function V, where gamma is the classical trace operator. And I was about to write. It's a classical trace. Okay, by now we know that there is such a solution, so we can pick if we have it. Now the question is how to cook up non-local problems and what can you prove? So let's call it a theorem, and I think it is theorem 25. And the theorem says the following. Given S in 0, 1, there exists KSXY, or let's say KS from RD to RD minus the diagonal, producing a non-negative number, which is symmetric with nice upper and lower bounds. And these are exactly the ones that you had seen before. So here now you would expect the Levy measure, remember, you would expect this density nu y minus x, but I want to be in the situation of the fractional Laplacian, so it's y minus x 2 minus d minus 2s. So I claim there is Ks with this property for every s, for some lambda, for some capital lambda independent of s. So let's say this exists, so 1, but also there exists GS, which comes from the dual of the trace space, and FS, which is now the right-hand side to the non-local problem. Such that the variational solution US to the Neumann problem and here you check theorem 24. Satisfies the following. A, we get convergence of US to U in L2. And B, we get convergence of the energies let's say of the bilinear forms to the local bilinear form. And you want this to be true for every V, but V will be on the whole space. So here you have to restrict V to D. For every V in H1 of RD intersected with L2 of D2. That's the result. Now let me tell you what are the ingredients in the proof. Somehow, what do we have to do? We have to approximate all three quantities, right? So we have a limiting equation and you want to approximate this guy, and this guy. And of course, we have to be careful because you want convergence of the solution. So you want to be, when S goes to 1, very close to these objects. This part is maybe most interesting because using trace and extension results, it's very natural what to do here. I'll show you how to do it. Yeah? And then, of course, I'll show you also how to do this. Okay, this will come later. So what are the ingredients in the proof? First, you need the robust extension results. This is what I had called our lucid dream. Then you also need the robust Poincare inequality, which was your exercise, which you got 3 hours ago. Remember, robust means that constants stay bounded when S goes to 1. Now, then what we do, we given S and given capital F, we extend F and this will define, note there's a dot here, so this will then define an object in VS perp D RD. And analogously, maybe we should really write this here. We define E of G which will then be an object in the pool of the trace space. And the last ingredient is about the jumping kernel KS. And here I'll give you the explicit form, because that's maybe something you are very much interested in. I think this is correct. Somehow I wanted to avoid the constants, so maybe I'm looking at Torben and Gloria. So somehow I thought it's nice if I just do 1 minus S and not the real constant. Is it then correct this way? Maybe there's a constant missing right now. There might be a constant missing, right? So somehow, if you make exactly this choice, it might be that you get a multiplicative constant in your solution. But it's correct to think in this way. I think it's a good idea to think this way. And if there's a multiplicative constant, it's no good. So you might want to check the result. And also, I think you have to be careful about this guy here and this guy. Because this is rather you use a representative, I guess, right? F and G. So here, when I say extend F, so I think it's better to extend F, which is a representative representing F. And here, I think it is better to extend little g, which is a representative capital G. Yeah, and that basically are the main ingredients. But you also need to understand how to deal with convergence of sequences, of spaces, because in order to show that GS weakly converges to G, you need a notion of convergence of the underlying spaces, because they are defined on different spaces. So that's a space of functions on D complement, and you want that when S goes to 1, that this space converges to H1/2. But what does it mean that a Hilbert space converges to another Hilbert space? That's something that's not standard, right? So this was sorted out a long time ago, and I'm not sure I know a reference for this, but I think, I mean, I know, of course, it's Kuwei Shioya. And I think it is something about 2002, 2003, and it's communications of analysis and geometry or something. 2003. So they have a notion of convergence of spaces. I can make a footnote, I guess, here. And here you are then done. So these are all the ingredients that you use. Of course, there's a lot of technicalities, but it's very convenient because it's very explicit. So in particular, you give me A of x, I can build K S x y, and I can look at the non-local problem in a very similar way to how I look at the local problem, how the coefficients interact and so on. So let me, maybe I'll then, since I'm done here, I can also put it here. Let me say a sequence of Hilbert spaces converges weakly to another Hilbert space. I think if there exists a dense subset and a sequence of linear operators no, they shall go to Hn. With the property such that for all u in the dense subset, you have that if you apply phi n to u, that this in Hn converges to u in H. Yes. That's it. So this is very helpful if you study gamma convergence or Moscow convergence when the underlying space changes. And if you want to know how to apply this to gamma convergence or Moscow convergence, there's a very good reference by Kolesnikov. I don't know the year. So Kolesnikov, as in K-O-L-E, Kolesnikov has a very nice paper when he explains an extension of gamma convergence to underlying variable spaces using ideas of potential. That was chapter 5. As you requested. Okay, it took 20 minutes, so I have now 40 minutes left. Okay, so chapter 6. I will not repeat the title, it's already there on the blackboard. So in the late 19th century, people like Poincaré and others, they studied potential theory and balayage theory. And of course, they began with dimension 2. And Carl Gustav Axel Harnack came up with the Harnack inequality. The Harnack inequality then didn't interest anybody for 40, 50 years. Even in textbooks in the beginning of the 20th century, it was not mentioned. They did mention the Harnack convergence results for harmonic functions, which follows from the Harnack inequality. So that Harnack convergence result was very famous. And if you look at textbooks from the 1920s, you see this result mentioned all over the place. But the Harnack inequality itself was not mentioned. And it became super important then in the 60s, 70s, and up to now. And Carré mentioned this De Giorgi-Moser-Nash theory, and now you will get let's say, a super fast run through this. Okay, so what is Harnack's inequality? So this was 25, I guess, right? So that should be 26. So the classical Harnack inequality. He never proved it in RD, but that's not important. Let's fix some notation maybe, because then it's much nicer. So there is a positive number C such that for every non-negative harmonic function in a ball, in any ball, in a ball, let's say, to be, the following is true. If you go to the original ball, so that's the ball with the same center and double radius. Yeah. Okay. So you have harmonicity in a large ball. You have non-negativity, and then you know that the ratio ux divided by uy is bounded from above and below, right? It's a symmetric thing, so you can interchange x and y, so you can divide by ux and y. So it's totally symmetric. An immediate consequence is u is not zero. If u was zero, this would be wrong. Yeah? So you deduce that u is not zero as a consequence. Okay. As I had said, somehow this was not so important, but the main application was the Harnack convergence result, but let's skip that. So then, many years later, yeah, it's part of the De Giorgi-Moser-Nash theory, but I think here it is really fair to say Moser, and then maybe that's 61, not 69. He extended this result greatly to the following. There is C positive such that for every ball and every solution U in H1 of the larger ball to the equation we had A there, so why don't we use A? Oh, come on, let's use A. In the larger ball. And you want a non-negative solution. So that's important. So such in every non-negative solution. So there's such a every ball and every non-negative solution we have the same assertion for all x and y in the ball. U of x. This is true if A is uniformly positive definite. So I hope it's now I erased it. That's a pity. My idea was to use it. I wanted to use it from chapter 5. Didn't work. So such a revolve, non-negative solution, blah blah blah. This provided A is bounded and uniformly positive definite. So this was the assumption that you had seen in chapter 5. Now, I think you will agree with me that this is a remarkable extension, because here you have harmonic function. So that means here you have in this ball you have Laplace u equals 0. Whereas here you have an equation in divergence form with bounded measurable coefficients, and you need to formulate it in a weak sense. That's why we have the solid space here. So obviously this is a great extension. And now what is it good for? And this is then the key point of the De Giorgi-Moser-Nash theory. An application of this is that in B you get Hilder estimates. So that would be a corollary. And this corollary had been found by Emil De Giorgi already in 57 and Nash in 58, I guess. And we can formulate it like this. Solutions, here you don't need non-negativity. Solutions U in H1 of 2B satisfy such a bound with a constant independent of U and basically of B. No, I mean, if you scale it, of course you will get a constant of U and the center of B. I mean, it's an equation of second order, so you can rescale it. You can replace ux by u lambda x, and then you will kick out something, and you have to see the scaling here. But it's infinite. Now, okay. So this is then an a priori estimate in Hölder norms, and this is the key to nonlinear problems, because this happened exactly in the lecture of Xavi, that he had a very complicated equation, and for some auxiliary quantity, he showed this auxiliary quantity satisfies a linear equation if you accept that the coefficients depend on the solution again. So let me make the statement again. So here we say every solution to this equation has this property. Now, if A depends on U, you can still make this assertion as long as A depending on U is uniformly positive definite. Because we are looking at a given function U. That means if you have a function U and you enter still coefficients in a very complicated way, but you're lucky that this object is still in X uniformly positive definite, despite the fact it depending on U, you still have the result, you have that result. And this is the key to a large class of nonlinear problems in divergence form theories. Yeah. And if you then go to harmonic maps, and so this is they all use these results. Okay, now this is about non-local things, so I need to tell you why how this is related to non-local problems and what is happening with non-local problems. So think about the same problem for the fractional Laplacian. You can take the Harnack's inequality. You can take also like the Moses result. Is it true for the fractional Laplacian? We can maybe even use that theorem. Let's not do it. So, theorem 28. There is C positive such that for every non-negative sufficiently regular function U defined on RD satisfying harmonicity with respect to the fractional Laplacian we have this result. I think it was not stated like this, but it certainly included in the paper by Marcel Ries from 1938. It's like the same result, right? Do you see a difference? There is one difference between this result and that result. Yes?
Yeah, it's all space. You have the
Okay, so you say this symbol is different. It's not 2B, it's RD. I agree. But maybe you wanted to...
the non-negativity.
Yeah, exactly. That's the point. So, the point is, I somehow tried to trick you because I put it here. We assume U is non-negative in all of RD. And that is, of course, now something which you could somehow try to change. So this means that U as a function of RD is non-negative. So it means, or if I turn it into a question, can we drop the assumption u greater than or equal to 0 on RD? How about u greater than or equal to 0 in 2b? That would be a fully complete statement if we just wrote u is a sufficiently regular function defined on RD, but is non-negative in the large ball. It satisfies the equation in the large ball. We get the result, right? So that would be a possible extension of the Harnack inequality, and somehow, yeah, is it true? It would be a much stronger result. We have somehow a much weaker assumption, but it's not true. You cannot reduce it to this. And this is the beginning of an interesting story for non-local operators. And I guess that I ended up as a mathematician is really very much related to this question, because I was able to answer this question, and it's not a very deep question, yeah, but somehow it attracted quite some attention, but not because of the proof. The proof is horrible, but the picture was good. Yeah, I had a very good picture. And it's also a little bit funny that it is published only in a preprint at the University of Bonn of our collaborative research center. And this preprint number 360 of our SFB 611. And it's really funny that people really cite it like this until now. So it goes like this. You give me number S, and then I produce a function u, which is continuous and bounded on RD, with u on the, let's say, the large ball. So you give me a ball, and B ball. So and B. Let's do it in B1. Come on, it's a translation invariant operator. Somehow would be really stupid to make it faster. So u in B1 is C infinity of B1. There's u, which is smooth in B1 with the following properties. It satisfies the equation in B1. It is strictly positive for x in B1 if you remove the 0, and it is 0 in 0. So Harnack inequality under this weaker assumption would fail, because this function here is non-negative in the ball B1, right? It's 0 or positive. It is harmonic in B1, but it cannot satisfy this ux less or equal to constant y because it is 0 and 0. This is a really a one-page proof, or I think our colleagues in Wrocław, they would make it a 3-line proof. The following picture tells you everything. I got very excited. I even put it in a computer at the time. I remember that. So I give you the profile. It's a rotational symmetric function. So this is the ball B1, and you want a harmonic function. The harmonic function we can think about being produced through data in the complement, and then by Poisson extension, right? So you prescribe data here, and no matter which data you prescribe, if you are in our nice place, please, there was a joke, then you get a solution inside, yeah, by the Poisson extension. So now let's play with that. So if we have this data, if we just put 1 everywhere, what will be the solution? The solution will be, of course, 1. So now I want to bring down the function here. How do you do that? And the idea is that somehow, okay, you prescribe maybe 1 here, and you prescribe some negative values here. And I do this also here. So we prescribe values 1 and maybe -1 and 1 and -1, and then what happens? The harmonic function at the boundary still respects the 1. So can we think probabilistically? It's much easier. So probabilistically, you sit, let's say if you want to compute this value here, you sit here, what's the probability that you exit by a jump into this area where you would catch the negative values? The harmonic measure sits on the complement, so we integrate against the harmonic measures, so we care about where the process will jump to. So it is much more likely that it jumps here than there. In particular, when you are here, you will exit through this boundary, you will catch the 1. That's why your solution will be, of course, 1 here. And then somehow, when you are here, you have some chance to reach -1. So of course, many paths will reach this guy, but other paths will reach this guy. So the value here is significantly smaller. And once you realize this, then you just play. You can play with this radius and this radius, or you can play with this height. And then what you do, if you have a lot of time, I don't know, then we produce such a function. And then it's non-negative, and it's 0 here, and harmony is 1. Now that was not what I wanted to tell you, but it is a nice introduction, because it tells you that these non-local operators, they are non-local, so long jumps, long-range interactions can mess up results. They can mess up a lot of things. And we recently found that they can mess up something which was not expected. That is the last thing that I'm going to tell you now in the last 20 minutes. So now we go to the parabolic situation. So what about the heat equation? Do solutions to the heat equation satisfy a Harnack inequality? Solutions to the heat equation sometimes are called caloric functions. And this turned out to be much more complicated, and the proof was only given in the 1950s by Hadamard and Pien. And then Jürgen Moser in 1964, he gave a proof, which was incorrect at the time, but he gave a proof of the parabolic Harnack inequality, and then in 1967 and 1971 he enhanced it. And he did it, of course, not for the heat equation, but for general divergence from operators. So now this is not so. I mean, okay, okay, now we have to do it. Otherwise, doesn't work. What about solutions to the heat equation in a time-space cylinder, or more generally, okay, now some little notation. That's going to be quick, I promise. For T naught positive and R positive, we define time intervals. The time interval IRT naught is just the interval where in time you go back by R squared and you go backwards and forwards by R squared. Now, we also need the upper part. That means we only go forward in time, and we need the negative part where we go backwards. Now, you might wonder why I put r squared, and that would be a good question. That relates to the scaling of the heat equation. Now, here's the theorem. And let's optimize also the presentation. The theorem is then 29. And this is Hadamard and Pini give so independent works. I did look up the years, it was around the 50s. And this was for the heat equation. So, and it was Moser in 1961, 64, yes, for uniformly elliptic equation. But the works of DeGiorgi and Nash from 57 and 58 are super influential for Moser's work because one could argue that Nash knew about it already, but I guess he knew a lot of things. So here's the result. In the same framework, spirit, there is C positive such that for every R positive, T naught positive, and X naught, every non-negative solution U, yes, of course, weak solutions, where do they come from? L2, L infinity, L2, L2H, and so on. Shall you write that really? You know where weak solutions come from, I assume. So L infinity, L2, so this is space and time and space. And they put the domains, but you will see it now. I mean, it's much more elegant not to write anything. Negative, so let's do like this. Weak solution. To the equation dtu minus divergence A where Q equals 0 in a cylinder satisfies the following. The soup of U in I minus of R T naught minus R squared. I will make a picture, of course. Satisfies this. Let's explain this. First, why soup and int? Where does this come from? That's already here. You know, look at the Harnack, or what was it, the non-local Harnack or whatever. So once you have this for all x and y, you are welcome to take the soup in the ball B, and you're welcome to take the inf on the other side, right? So because x and y are completely independent, so they would be the same statement. Yeah. Okay, so soup and inf is here not the issue. Yeah. And of course, if it's a weak solution, it has to be the essential supremum, the essential infimum. Let's not care about this. But more important is what's going on here. So here you see B R of x naught. Time goes in this direction. The point T naught is I plus R. I run forward in time. So this is here is T naught. This is T naught minus R squared. And here I chose the soup of U where I go from T naught minus R squared into the past. Yeah, so don't miss that point. Actually, Moser even has a comment on this. A little interlude, a little quick interlude. For second order PDE, you need this gap. And everybody believes it's true for non-local operators, because all the proofs work with such a gap is not true. For non-local equations, you don't need the gap, but almost no one knows. It's really that's true what I said. Okay, so the heat equation is here. What does that mean? So you have somehow your initial condition, heat develops in time. What does this result say? It says once the heat is above a certain threshold, it will not go down because the inf here is estimated by the soup here. Yeah. So here you have the inf, and here you have the soup. This result has similar applications. You get interior Hölder regularity estimates, which was then very important. You can show heat kernel bounds, upper and lower bound, the famous Aronson bounds. So shall we mention them? Yeah, when he pointed out the paper of page 2. So it's, let's say, a core or key results from it. Okay, now what to do for non-local operators? Now, basically, you want a result like this also for non-local operators, and several communities have spent a lot of time. It started in the year 2002, and people working with stochastic analysis and these Dirichlet forms and their processes were extremely successful, and it took some time before people from analysis were able to catch up. Yeah, and I think now I shall tell you the final result for non-local operators, which is, I think, the optimal result. And there's even counterexamples in the paper that show that you cannot enhance the result. Here, note, I didn't say that the solution needs to be bounded. I said a non-negative weak solution. And there was some in infinity, but there was in time with values in L2. So no one said that solutions need to be bounded. The first step in the proof of this thing is to show that solutions are locally bounded. So you first prove a local L infinity bound by some L2 bound on an extended or larger board. So boundedness of solution is not required. For all results, concerning non-local, boundedness had been assumed all the time through, and you can remove that. And you can even enhance the Harnack inequality for non-local operators, which is very cool. So the last thing will be then 5 minutes to give you the final results in this direction. And then, of course, I'm welcome to answer questions, or we can meet here tomorrow. Is it open, the institute?
Go to your car.
I get a special card. Thank you. Okay, so and this is the source for this is in a recent paper with Marvin Weidner, which you find on arXiv. So there's several papers, and this is called the parabolic Harnack inequality for non-local equations. Not so surprising. So the operator that we have is allowed to depend on time. So not surprising, there's a principal value integral, and you see, of course, u of x minus u of y, but this time you can depend on time. I don't depict that it depends on time, but you can also, because this operator acts in space only, so you don't have to put time, but you may depend on time. It will depend on time. Whereas our kernel does depend on time. Dy. Now let's formulate the result in a very simple setting, where we assume that these kernels are bounded from above and below by the classical kernel from the fractional Laplacian. And of course, we put the 1 minus s because we want robust results. We want results that, at least informally, are continuous and recover what Moser did. Yeah? And I could explain now in detail why all probabilistic techniques are not able to do this, because they have a certain property of their jump process, the one-hit jump property, which destroys robustness. So this is the standing assumption for all x and y, and let's say for all t if you want. And then we can prove the theorem, which is in 30, and it. Now we have a different scaling. Yeah? So I told you that the r squared was because of the parabolic scaling of the heat equation. Now we have to change that. So I'm somehow sorry, but somehow what I will do, I will write a 2s here. No good. So I put the 2s here, the 2s here, and the 2s here. This is now my definition, but
Yeah.
right?
You have to write it in the left.
Yeah.
You don't have to write.
Yeah, I mean, this is horrible, right?
Yeah.
Let's just not do it. So now we have changed that notion by putting 2s to s. And then the result is for every r, for every t naught, yeah, it's basically the same result. I mean, yeah, I can copy. Let's formulate it in the easiest way. Yeah, every There's a constant. There is C. We should say this too. Yeah? There is C positive such that for every RT naught and X naught, every non-negative, that's a globally non-negative. So I don't want to trick anybody. So we go back to the globally non-negative, and we can discuss in length how to remove this by introducing tail terms. Every globally non-negative solution U, weak solution, U to the equation dTu minus LTu in I for R T naught B for R. We can even say for every. There's C such that for every S in S sub star 1, so we want the robustness, and that's actually very important. So I'm sorry that it doesn't look so beautiful in the paper. We have that differently, but I like it more like this. So let me read again. There's a constant such that for every S in this interval, for every RT naught X naught, every globally non-negative solution, weak solution U to this equation, satisfies this property. No. Sub U and I are minus, now we go back T naught minus R to S, and actually we do this only for technical reasons. It's not optimal, but our technique doesn't allow to remove that gap, but we know it's true. Yes, and now we have plus, please don't forget we changed the definition of these intervals. Yes, so this will be the result, and let me finish with some concluding remarks. Theorem 30 had been known or is known for bounded solutions where boundedness follows on this result. And known for bounded solutions and in a non-robust fashion. One can weaken the assumption of non-negativity of global non-negativity, I should have said, to local non-negativity, which will then have tail terms appear actually on both sides. But the most important one is on the right-hand side, leading to a modification of parabolic Harnack inequality by the yes, okay, tail terms here. And the third result, which is part of the project, which you cannot see, L1 assumptions of the tail are not sufficient if there's a counterexample. So, but let me not put it here because it would not be understandable from what you have seen. So these two remarks are understandable. But if you like that subject and if you are interested in parabolic Harnack, then please go to the paper. I have not mentioned any literature. This is of course a problem because many people in several groups have contributed over the years to this result, and there are versions, of course, of this result, and we try to do a good job by mentioning all of them and say what is the difference and so on, what other people did. So please don't think that somehow I just somehow came up with this result. And it's of course rubbish. It's just can be seen in as a final result in a long list of results. If you want to learn more about Harnack and Hölder, please invite me to your local university. And I'll come. Thank you very much for your attention, and thank you very much for staying with me through 4 lectures.
So when you move from global to local non-negativity, I assume you need to have some value in the recap.
Yes.
Do you need to assume some boundedness because the tail?
Yes, you need to make some assumption on the tail.
Yes.
And you need to have a little bit more than L1, and you can show that L1 creates a counterexample to Hölder regularity. We have an explicit counterexample in the paper. So if you want to go to local non-negativity, you need to assume that the tail terms, the parabolic tail terms, are in L1 plus epsilon, and epsilon to 0 does not give Hölder regularity. You can show by an explicit example it's false.
Any more questions? So, just before we thank Moritz again, I just want actually going to go thank Azahara and Mar and the team they have here helping them at I-9 for all the organizing they've done for this week. So, just going to give them a round of applause.
Azara, thank you very much for being flexible, for wonderful organization. So it was also not, I hope for the participants it was very good, but I think for the speakers it was very well organized and very nice to be here. Thank you.
So thank you very much. Thank you to all the participants, because without you, that was not possible. Thank you, of course, to the 4 speakers. You guys great mini courses. I enjoyed learning a lot. And okay, so most of you will be here next week. So see you soon. Enjoy the weekend. Reread all the notes you took. And for the one who has to leave, it has been a pleasure, and hope to see you soon. So now we can leave.